Good afternoon, everyone. Thank you for attending today's session, Next Generation Commercial Water Heating. I'm Jeff Wicks with the Northwest Energy Efficiency Alliance, and I'll be moderating this session. Before we get started, I'd like to cover a couple of housekeeping announcements and then quickly move into our speakers' presentations. As a reminder, your screen is customizable utilizing the various widgets found at the bottom of your screen. Presentations can be downloaded as PDFs from the resource list in the menu. Attendees are in listen-only mode at this point, but you can submit questions through the Q&A during the webcast, and the presenters will be answering those questions following the presentations. All presentations will be available for an on-demand viewing within a few days on the Engagement Hub, so stay tuned. Zoom discussion rooms will be offered afterwards, and that link will be on your screen as well. Be sure to complete the ACEEE Hot Water Forum survey on your last webcast. It helps ACEEE do some planning for the future. As part of the steering committee, I'd encourage you to do that. It helps us to really understand what was valuable and what wasn't. Also, there's a special announcement that ACEEE would like some feedback regarding this year's Hot Water Forum. You'll have access to this survey all this week in your console. Please take a moment afterwards, and after watching your last webcast, complete the survey. For those who do, you'll receive a $25 discount off your registration off the 2022 Hot Water Forum in Atlanta. Last, I'd like to thank our sponsors and partners for their support of the Hot Water Forum. It's essential for us to bring this to you. As we get into this session, I'd like to set the context of a framework for this discussion. I'd like to share with you some work that we're doing at the Advanced Water Heating Initiative, specifically on central systems. The overall team goal there, as developed through their logic model, was high-performance heat pump water heaters are installed in 90% of new multifamily construction across the U.S. by 2026. We did develop a draft logic model for this, and we identified 4 different barriers or opportunities, and we're hoping that the speakers today will address parts of them. So the 3 barriers and 1 opportunity we're looking at is entrenched supply chain, underdeveloped distribution network ability. Current business practice is focused on components, not a standard solution. The second one is a split value proposition, low awareness of efficient options to customers, high first costs. The third barrier, lack of accepted performance specifications, no adopted comprehensive sizing tool, inconsistent codes, standards, and test procedures. One of the opportunities that we're trying to leverage here is there is a large movement underway on the coast, but also sweeping the nation on decarbonization. And will that help accelerate the adoption of a standard heat pump water heater in central units? So I'm going to be introducing each one of our panel speakers today, but I just want to give you a rundown of who's going to be here. Ryan Hamilton, the president of Nyle Water Heating out of Portland, Maine. Kane White, the director of commercial product management at Mitsubishi Train out of Atlanta. And Lynn Mueller, the CEO, president of Shark Energy Solutions out of Vancouver, BC. So we're covering a large swath of the country and lots of different applications and ideas. We'll start first with Ryan Hamilton, who's the president of Nyle, an entrepreneur for more than 20 years of professional experience in challenging markets around the world, developing a commercialization transformative solution. He cares deeply about creating and maintaining a people-focused work culture, aspires to be a living example of his desired state for humanity, and strive to do more than he wishes other people could do. Ryan will be presenting what Nyle is doing to take the central heat pump water heater to the next level. He will provide some case studies in student housing, senior living centers, and some additional benefits of heat pump water heaters. Ryan, please take it away.
All right. Thank you, Jeff, for the introduction and for the opportunity. And thank you and hello to everybody who's watching and listening. My name is Ryan, and as Jeff mentioned, I'm president of Nyle Water Heating Systems. I really enjoy the work that I'm doing, and as Jeff was mentioning there in the introduction, I really try to embody, the things that I'm working on, and the work that I do is my passion. And really, I wake up every day, thinking about climate change and mitigating the effects of climate change, reducing our carbon footprints, and I'm fortunate to be able to work in this industry and actually, have an impact and put that passion to work. I want to present on not only the technology and our company, but where things are heading for this technology, and being able to really accelerate the transition to fully electrified and decarbonized built environment. So a quick history on Nyle. Nyle Systems is a manufacturer of a large commercial and industrial heat pump based systems. The company got its start with dehumidification drying technology that was developed in response to the oil crisis of the late 70s. And naturally, that technology provides many benefits, not just to drying applications, but also into other types of processes like heat pump water heating. So the company's been producing a line of heat pump water heaters for a little over 10 years now. And generally speaking, there are two types of split heat pump water heaters on the market that are available. You can see air source heat pump water heaters and water source heat pump water heaters really make up the primary two categories for this technology. As it's been mentioned in many of the other presentations, storage tanks are a critical component of a central heat pump water heating solution. And in fact, as we're designing and training others to design central heat pump water heating systems, we talk about it as a storage-centric system. Somebody earlier was raising the question of running the heat pump all day and using the storage device to absorb the energy and release the energy as needed. And that's really how a heat pump system is designed to work, with the heat pump operating about 16 hours a day. Next generation heat pump water heater platforms are being designed, developed, certified, and released to market over the coming years, really starting this year, where we're starting to see some low GWP systems being developed and released. There's already a couple of CO2 systems out there that you might be familiar with. Now, what we're talking about when we mention low GWP, this has to do with the global warming potential of the refrigerant. Just to provide context on that, the global warming potential of CO2 is seen as the baseline. So it has a measurement or a rating of 1.0. And the heat trapping capacity of any of these other gases is determined as it relates to that baseline of CO2. So you can see that 410A has a GWP rating of over 2,000, and 134A has a GWP rating of over 1,400. Manufacturers, Nyle included, are developing a line of water heaters that utilize low GWP refrigerants, and those will range from CO2 to some others that are utilizing a 1234 natural refrigerant, and then there are some blends available. At Nyle, we have selected 513A as the refrigerant of choice, and that's going to be integrated into a new platform from the ground up that's going to allow for a wider operating envelope and compact footprint. So one of the challenges, Jeff, that you mentioned is the entrenched supply chain, and how are we going to overcome the fact that a lot of water heaters, especially in the existing building stock, are replaced in an emergency situation, which means, we need these types of products out there on the shelves and in the market ready for deployment. And we also need contractors and engineers to be aware of the options and have familiarity with them, and also know that they're readily available. So what we're seeing in the marketplace is a quick transition to providing modularized split heat pump water heater systems. As I started thinking about how to describe this packaged approach, it dawned on me that there are already integrated solutions. And so I thought I might get the question, why are we just heading towards an integrated solution with these split type systems? And really the answer is no. I think we're always going to have a split approach, especially for these larger type systems where you can't always have the heat pump compressor unit co-located with storage tanks. And California is a great example of that, where it often makes the most sense to have the heat pumps on the rooftop due to space constraints and the mild climate. And naturally, you don't want to have thousands of gallons of heated water storage on the rooftop due to seismic concerns, and so those need to go on a ground floor. Oftentimes, those two things won't be co-located, and so that's a good example of why, even though we're going to be bringing systems together and offering tanks and pre-pipe systems with pumps and control valves and such, there's still going to be this need to split things apart, especially with larger systems. So the most common use cases for these types of systems are going to be where large amounts of hot water is consumed on a daily basis, where it's repeatable and predictable. So multifamily buildings, such as the ones in the picture here, where we have an installation of Nyle heat pump water heaters providing all of the hot water for the occupants of those buildings, college dormitories, hotels, and other applications where hot water is consumed on a regular basis. So for some application examples, this is a student housing facility in San Francisco, just to kind of provide some pictures and context for what these systems look like in practice. You can see that this is these 4 heat pump water heaters are serving a building with over 300 occupants, and it has 4,400 gallons of storage on the ground floor, and 4 heat pumps on the rooftop that would total a little over 1 million BTUs an hour. Another nice example, this is actually the pictures of the first buildings, the multifamily buildings. This is a San Francisco student housing. Again, 320 occupants with about 5 C250 air source units, and these are ducted to the outdoors. This is a nice application or use case where there's excess heat available in a mechanical room. So these are co-located with boilers and are able to scavenge some of the waste heat that comes off of the heating boilers for the HVAC side, and it actually tempers the room down to a more reasonable 60 to 70 degrees instead of being up at 90 degrees when the boilers are running. So that's a nice way of sort of an indirect heat recovery function. You can also co-locate heat pump water heaters into a space where you would have waste heat coming out of an ERV or fresh air exhaust as well. There are other applications for heat pump water heaters, such as reheat on an HVAC type system where you can't overcool the space. These units are installed in a warehouse in Hawaii, where they're providing temperature and environmentally controlled storage for shipments. And so these units are able to reclaim some of the heat off of the chiller return and provide that as a reheat. And then looking at these systems from a high level perspective, just kind of at a building concept, how are these units applied and what are some of the options? So the first one that we have here is integrating water source heat pump water heaters into a system that has a condenser water loop for the HVAC. So you would have water source heat pumps in each room or in each space, as they're shown on each floor here. And then depending on the climate, you would typically have either a cooling tower or an air-to-water heat pump water heater to maintain that condenser water loop between 80 and 90 degrees. Usually it's either going to be a cooling tower and a boiler, or this air-to-water heat pump reversing unit that I'm showing here. And in either case, the domestic water heat pumps will pull off of that condenser water loop and create the hot water from that. Now, the nice thing about that is you can see the really high summertime COP, and that's a result of a heat recovery approach where the water source heat pumps are dumping their rejected heat into that condenser water loop to cool the space. And then the heat pump water heaters are going to grab that heat and reconcentrate it and lift it to a higher temperature and store it in these on hot water storage tanks. This allows for a very, very high overall system efficiency, especially in the warmer months. Another nice example is, geothermal. This is applicable for any climate, especially in colder climates where we need to lean on a geothermal loop to provide tempered water temperatures, especially in colder winter climates like in Canada and here in New England, where we can see temperatures down below -20. So it's obviously most efficient to use a ground source type system. And then another one that we've seen deployed very successfully is utilizing a subterranean garage or even ground level, depending on the climate. Again, it's really going to drive a lot of the system design, whether you're up in Canada or in San Diego. But in this case, something like this is pretty successful in a Seattle type environment where the temperatures can dip into the 20s occasionally. But generally speaking, you're not going to spend lots of time in the 20s. So this is a way to let the parking garage and the ground provide some heat to the system. And then finally, sort of the California style system where it's all air source and nobody's worrying about trying to recapture waste heat out of the space. We simply have independent systems with an air source VRF providing HVAC. There's very little opportunity to integrate with VRF systems and reclaim waste heat and put it into domestic hot water production. But again, with mild climates, there's still relatively high seasonal efficiency with a system like this if the temperatures are warm enough. So looking ahead a little bit now, there's been a lot of talk on this year's presentations about utility integration and demand response and the grid services that can be provided by water heaters. This is one of the things that actually really piqued my interest and got me involved in this segment of the industry. I came out of solar plus storage into heat pump water heating, and this is one of the reasons why, because I see this opportunity for heat pump water heaters to play a role in energy storage and utility services space. So one of the first things that we've done is integrate the controls capabilities into our heat pump water heaters by partnering with Packetized Energy, who operates a platform of aggregated loads for utilities. And so by integrating that technology into the heat pump water heater, not just as an accessory, the response times are faster, and there are some additional services that can be provided to grid managers. But the high level thinking here is, there's a visual here that shows kind of today's peaks and demands on the utility. And then the yellow line shows, of course, the solar production of when renewable energy is being produced. And that a lot of those peaks fall outside of the times when solar is produced. So historically, we'd be talking about batteries to store that energy so that it can provide the electricity needed for those loads outside of the production time. But what we're seeing is possible with heat pump water heaters, and what really gets me excited is the fact that we're connected to large amounts of energy storage. A BTU is a kilowatt hour. Energy is energy. And so by being able to store energy during times of renewable energy production and do things like advanced load up, increase that temperature to 160 instead of 140, we can really absorb that excess renewable energy and then use it on those predictable, repeatable loads, which happens to be hot water. So there's no reason to convert to electricity and then to running a water heater. You just simply run your water heater and store the heat energy so that it can be used on demand. That's the most efficient approach for this type of an operation. Now, there's, of course, a value in that. And this is where I think there's a lot of opportunity to overcome the inherent challenges that we have in this marketplace. Again, talking to your questions, Jeff, about how are we overcoming the barriers to entry into this marketplace? And one of those is high cost, high upfront cost. And then because of the low cost of energy, of gas and fossil energy compared to electricity, the cost savings of operation are often normalized or eliminated. So developers and owners look at a high upfront cost and no ROI. And this is one of the things that can actually start to change that and turn this into a financially sound decision for developers and owners if the heat pumps can start to become revenue generators. So that concludes my presentation. Hand it back over to you, Jeff. Thank you again.
Great. Thank you, Ryan. There is one question in the chat that's very much germane to just you, and that is, does Nyle have a line of CO2 system in the works, or is it planning to in the future?
Planning to in the future.
Okay, great. I think there's some other great questions in there, but I'm going to move those along. We're running a little bit behind. Our next speaker is Kane. Let me just move you on here. There we go. Kane White with Mitsubishi Train. He's the Director of Commercial Products Management at Mitsubishi Train and is responsible for all new product developments and works closely with Mitsubishi factories globally. With over 22 years experience with Mitsubishi VRF technology, including service management, product management roles, upon moving from the UK, you might hear this in his voice, to Texas. I don't think I picked much of that accent up when I heard him. Kane managed the Southwest Business Unit and the service department, and finally moved to Atlanta, Georgia, to take on the product management role for commercial product management. He has progressed through the department and now leads efforts in VRF, DOAS, ERVs, and hydronic products. Kane is going to present what Mitsubishi Train is leveraging their solutions from other worldwide markets and what the U.S. market needs for a modular solution for multifamily. So take it away, Kane.
Yeah, good afternoon. Thanks very much, Jeff, and thank you to everyone for joining. So I'm going to run through a new product that we're promoting under the banner of Heat2O. So you'll see reference to Heat2O and also QEHV, which is our model name. But this specific product that I'm going to be talking about today is a heat pump water heater using CO2, a natural refrigerant with a GWP of 1. Very efficient system, COPs up to 4.11 at DOE test conditions and higher than that at various other conditions. We can supply hot water up to 176 degrees Fahrenheit, even at ambient temperatures as low as -13. Maintaining 100% capacity down to 36 Fahrenheit. We'll also have BACnet connectivity. So using an external Mitsubishi Electric control panel, we can interface with a building management system using BACnet. We can also have a cloud-based access cloud solution to monitor the system, monitor the entire building or a number of buildings from the cloud, and then also gives us access to demand response. So we're able to connect through a CTA 2045 module and communicate with utilities and decide the best possible way to operate the system and at what capacity. That brings me on to the capacities itself. So we have one module capacity of 40 kilowatts or 136,485 BTUs, but we can actually operate the unit at 3 different capacity settings. So we have the 40, 50, or 60 kilowatt settings. The compressor within the unit and the pump within the unit are capable to operate in all 3, depending on ambient temperature. And we can theoretically go up to 16 of these units piped in parallel, which would give us about 2.183 million BTUs of a maximum system size. So just looking at the unit itself, we've got the chassis of the unit. It looks very similar to our VRF product, with our fans at the top there blowing exhaust air through the top. You can see the compressor to the bottom right. It's a pretty large CO2 compressor. We have an inbuilt inverter-driven water pump, so we control the speed of the compressor, the speed of the pump, and the speed of the fan as well. So a lot of regulation within there. Inlet and outlet connections, we have what we call our gas cooler, which I'll come on to shortly. Obviously the fan motor at the top, and then various control sections with control boards and electronics. So the heat exchanger, the primary device exchanging heat between the refrigerant, the CO2, and the water. So we utilize something called a twisted spiral gas cooler. It's patented technology, double wall construction. And we have 6 of these located inside each unit. So basically we have a twisted spiral pipe, a copper pipe, which is a larger diameter pipe, which is used for the water to flow through. The water flows from left to right. And then on the opposite side, flowing from right to left, we have 3 smaller diameter refrigerant pipes wrapped around that larger diameter pipe. The design of this enables a couple of things, really, to maximize heat transfer between the refrigerant and the water, and also to kind of create a spiral or vortex effect as the water passes through. So this cuts down on pressure drop and increases efficiency, and also, because of this design, helps to kind of reduce the overall footprint of the unit itself. So we utilize something called flash injection technology. This is something tried and tested, been used in VRF and some of our other products around the world for many, many years. But basically, in basic terms, we're able to operate the system down to -13 because of this technology. So what we're doing is in lower ambient conditions, the issue you normally face is that you'll find a low suction pressure on the refrigerant side, which means a high shell temperature or a high compressor temperature. And if the compressor gets too hot, then obviously that's dangerous for the system and also restricts performance. So what we do is we can operate the compressor at a higher frequency or higher speed while injecting refrigerant through an LEV or linear expansion valve into the chassis or into the shell of the compressor itself. By injecting the refrigerant into the compressor, we raise the suction pressure and we also raise, therefore, the discharge pressure, the discharge temperature, so we're raising the temperature of the water at those low ambient conditions, but we also cool the shell of the compressor down. And this is something that's controlled via our inbuilt logic, so nothing needed to add to the system, and we can continue to operate in these conditions. And actually through testing, we've actually had systems operating in Scandinavia, in Europe, down to about -35 degrees Fahrenheit. So with the CO2, we're able to operate at some very low temperature conditions. So next up, we also have an overall system schematic. So with this schematic, this is how we'll kind of be incorporating our units into the building system. So we'll be having a plug-and-play package set up with our QEHV or heat-to-O units. You can see to the left-hand side of the schematic. To the right-hand side, we've got a secondary heat exchanger. To the right of that, we have an inverter-driven pump on the secondary side and some thermistors. And then we have our storage tanks. And we're following the approach of having primary storage tanks to store the main volume of hot water required for the building. And then also a swing tank approach, which is the tank labeled ST3. That tank is taking care of the supply of hot water through the mixing valve to the building, but it's also separating the hot water recirculation load from the primary storage load. So the hot water recirc from the building flows back into the bottom of the swing tank, and then from the swing tank back out through the mixing valve and back out to the building. And by doing that, we're able to maximize the efficiency of their overall system and by basically having the maximum delta T, or the largest difference in temperature between the inlet and the outlet on the secondary side and the inlet and the outlet on the primary side of the system. With CO2, it's a very good refrigerant. From an environmental standpoint, it's excellent for low ambient conditions. But one of the key things is to maintain a large difference in temperature from the inlet to the outlet. And that's the reason why we're following this approach and this kind of standard with all of our systems. So along with that, we've actually worked with a US manufacturer to provide an engineered storage tank solution. So these tanks will be sized in 3 sizes, so 175 gallon, 285 gallons, and 500 gallons. On the swing tanks, we'll have 150 and 200 gallon sizes. We'll also have low velocity sparge fittings in the top and bottom of these tanks. So we're trying to, reduce the amount of mixing between the hot and the cold water, maximize the stratification, and keep as much usable hot water in that tank at any one time. So that's the purpose of those sparge. And basically, they're just, a pipe with holes drilled around, and it's reducing the velocity of the inlet and the outlet water. We also have up to 6 thermistor locations, so we can sense temperature of the tank at the top, at the middle, and the bottom. And we can use various thermistors to control the on and off, or the thermal on and off of the system. But we can also monitor the top of the tank and then additional tanks, so we can see exactly how much or how many gallons of usable hot water we have in a system at any one time. And lastly, you can use multiple tanks, obviously, in a setup, typically anywhere from 1 to 6 tanks. And that could be 6 500-gallon tanks or 6 of the smaller tanks. Okay, so next up this is a pilot project we're working on right now. So this is called Bayview, the Bayview Tower Pilot Project. It's a low-income multifamily retrofit project for the Seattle Office of Housing. Currently, they have 6 Rheem electric water heaters, so 102 kilowatts of electrical resistance elements that are being used. So obviously, highly inefficient and also very expensive and costly to run. They have 100 occupants in the building. It's about a 13-story building. So what we're doing here is actually going in with a retrofit setup. So we're looking to install our QEHV unit, secondary heat exchanger, and 2 500-gallon tanks you can see in the dotted line section on the right-hand side, top right-hand side of the schematic. All of that equipment is being manufactured and installed on a skid-mounted assembly, and that skid will be craned up onto a roof towards the back of the building. From there, we'll be piping the hot water in and the cold feed into the setup, and hot water into the building. Within the building itself, we have an existing hot water tank set up with those electric ream tanks I mentioned. So we're looking to reuse 4 of those tanks. We've got 2 different pressure zones in the building. We'll reuse 2 of the tanks for one pressure zone, 2 of the tanks in the other pressure zone, that's in the green and the blue. We'll feed the hot water from our system and utilize those existing tanks as the swing tanks. So kind of an example of how we do a retrofit, still keeping some of the existing infrastructure in place. And we're going to drop from an input capacity of 102 kilowatts down to a 40 kilowatt unit, but the input power for that unit is only around 9.6 kilowatts. So we're looking at a dramatic decrease in power input, energy usage, and carbon footprint. And the skid setup is something we'll be looking to roll out across the country. Next up, we also have, my slide's not showing here, so the slide's missing, but we actually have a field trial, or I'm sorry, a project in Japan. One slide's actually missing for some reason, but this is the system in Japan is a assisted living facility or a care home facility in Japan itself. The solution for that, they currently have an oil-fired system, oil-fired boilers. And basically, we went in there, took out the oil-fired boilers and went in with 2 of our QEHV units to provide the hot water for the domestic hot water usage. And then also we added in another product, which is what we call a CEHV, another future product for the US market that was used to constantly kind of reheat the hot water that's within the tanks and that's within the space. This reduced the overall energy bill by about 33%, moving from oil to a full electric solution. Maintenance was kind of dramatically reduced. And obviously, using electricity instead of oil, we dramatically reduced the carbon footprint of this building, this project itself. This has been installed in Japan around 10 years ago. We've got systems in Japan, in Europe, in other parts of Asia, Australia, and New Zealand that have been around for many, many years as well. So it's a proven technology, but something we're bringing to the US market. This is the slide that actually looks like they've gone opposite way around. So this was the care home slide itself, and you can see the care home to the right, and then some of the baths that they were using. So our technology is the bottom right-hand side of the picture. As it mentions there, we just replaced an oil-fired setup. Okay, lastly, just looking, Jeff had mentioned previously about barriers to market. So I'm just going to talk about the split value proposition he mentioned with low awareness of efficient options to customers and high first costs. So some of the initiatives that we're looking to take place, we're providing, in the process of providing educational videos highlighting the technology of Heat2O, an interactive sales / technical tool and software to help explain the system, an interactive tool to explain the system to engineers, architects, building owners, anyone that's really interested in having a one-on-one conversation with our sales team. We'll have dedicated design software to actually lay the system out. That's our DSB. We're also looking to interact with Ecotope's EcoSizer tool on the sizing side of things. We'll have an in-depth application design and installation guideline, industry-leading training with certification on the install and service side and on the design side. And we're also working with various organizations to help promote the technology, dealing with pilot projects currently in the US, so one in Seattle and one in California. We're also looking to help develop incentive programs. And kind of lastly, as I mentioned before, plug-and-play system with skid-mounted options with all components included, so we can provide a full domestic hot water solution and not just a heat pump product. So with that, I'd like to say thanks for your attention, and I'll pass it back over to Jeff. Thank you.
Thank you, Kane. Very timely. We do have one specific question to you, and this is from Rami. Kane, why is the additional heat exchanger required outside the unit where a double wall HX is already provided in the heat pump water heater and a pump is provided in the unit for constant flow through the unit?
Yeah, it's a good question. So worldwide, or at least in Japan and some markets, we use the product without the secondary heat exchanger. But we have certain water quality standards that we need to hit in order to avoid scale and corrosion. Based on testing in the U.S. market in various cities, Seattle, New York, Los Angeles, and various others, we found that the water quality samples kind of indicated that there could be issues with corrosion and that type of thing further down the road. So one of the things we're looking to do to be able to extend the life of the product, to cut down on any potential maintenance or service issues between the CO2 side of things and the water, to protect the system, is to provide that secondary heat exchanger. By doing that, we can offer extended lifetime, extended guarantees on our product, and any incoming water quality issues will be dealt with through a low-cost secondary heat exchanger rather than going directly through our product. So in theory, we can take the single straight through it, but we choose to use a secondary heat exchanger as mainly as a protection for our product itself, and to minimize potential downtime in the future.
Great, thank you. And if you have additional questions, please put them in the Q&A, and I'll try to gather them as we move into the Zoom meeting part of it too, if we don't get to them. So thank you very much, Kane. Next presenter will be Lynn Mueller, the CEO and president of Shark Energy Solutions, or Systems, in Vancouver, BC. Shark Energy Systems has grown out of an idea that Lynn had 11 years ago to the largest, most successful wastewater energy exchange company in the world. Shark Energy is a global leader in carbon reduction and energy efficiency. Previously, Lynn was president of Water Furnace International. Following that, he was president of Earth Source Energy, Inc. Lynn is responsible for a large number of advanced sustainable energy systems using the Shark technology, including a DC water headquarters, LEED Platinum, 170,000 square foot building, and lost my place in this, I'm sorry. The Wall Center, Central Park, a city block of 1,000 apartments in Vancouver, Borders College in Scotland, where Shark was able to offset 95% of the natural gas usage for the building heat. Lynn and Shark have been able to take the Shark system from concept to reality, and along the way, Shark has been able to develop working relationships with some of the largest energy companies in the world. Lynn has a strong passion for saving energy and recovers millions and billions of dollars worth of waste energy and goes down the drain every day. So Lynn continues to press hard on this quest and make use of energy for the reuse of energy as a norm for buildings in the future to reduce CO2 emissions and global warming. Lynn has 4 children, 3 grandchildren, so he has a personal mission to do what he can to make the world a more livable place for them. Lynn will be discussing a demonstration project that Shark Wastewater Systems worked with EPRI in a 60-unit apartment complex in Vancouver, BC. So take it away.
Thanks, Jeff. I don't have time to say anything because the introduction was too long, but I appreciate it. Thank you so much, Ryan and Kane, for a tremendous job there. Nice to meet Ryan the other day. And I just wanted to tell you about our Piranha unit, Piranha HC in particular. And we make energy recovery units from 25 kilowatts to 40 megawatts. So we have a broad scale of products. Great team worked on the EPRI project here, myself, Matt, and Eliza. Sponsored by some great utilities, Con Edison, Amaron, American Electric, TVA, and Con Ed. We're just in the middle of a bunch of projects in New York with Con Ed. But basically what we do is recover the energy that's leaving a building. So every day when people use their dishwasher, their shower, their laundry, prior to Shark, all of that energy would just go down the drain and disappear. So 10 or 12 years ago, I got the idea, that we could recover that energy. And I've had a 40-year career in the geothermal heat pump business. So I thought, the source temperature is pretty warm. The wastewater leaving a building is usually about 75 degrees Fahrenheit. So, if you had a geothermal heat pump with 75 degree source water, you'd have pretty efficient operation. So this picture just shows our Piranha HC unit in the mechanical room. It's about 32 inches wide and about 6 feet long, 4.5 feet high. And this just picture the storage tanks. So we have a very simple system to do this. The cold water comes in, goes through the Piranha first, exit at a fixed temperature. So this was the load on 50%. Water comes in there at about 50 degrees, and we heated it to about 100 degrees for 50% load. Then we did 75% of the load where we heated it up to 120. And then finally the 100% load right up to 140 degrees. We can put out constant output of 140 degrees. So we just constantly are recirculating the wastewater in a building. So we store about half of the day's sewage flow from the building in a tank below ground, and then we just use that so that we can have available energy any time of the day. One of the two most common questions I got originally was, am I going to smell it? And the answer is no, it's completely sealed. And then the second question is, where do you get energy at 2 o'clock in the morning when nobody's doing anything in the building? So that's why we store about half a day's energy in a tank below the building. And this particular building was 60 units, so we store about 2,000 gallons of wastewater there. And this is the Piranha HC has a second evaporator in it, so we can use the air conditioning feature as a way of getting heat for the hot water as well. So the unit provides wastewater heat recovery, air conditioning, and hot water all on demand. So you can see there that the building used about 2,000 gallons of hot water a day. The gas usage went down from when it was all gas there down to practically nothing when it was just the gas for the cooking. So in our test, we were able to show various levels of offset on that. The performance at the 100 degrees was about 4.5. At the 75% level of 120 was about 3.5, and then it just stayed about that for the rest of the operation through 100%. City water comes in here at 50, heat and leaving temperatures about 65 on that at corresponding temperatures. The runtime is a really neat thing here, is that the runtime, even on 100% of the load being done with the sewage heat recovery Piranha unit, the runtime was less than 14 hours a day. So it gave us that 10-hour time frame where we could stage the operation to not be on the peak times for the utility. And one of the features of the Piranha that's really innovative and is that we have a really state-of-the-art information gathering system on it. So we have real-time access to the unit via the cloud, and we record every second of the day's operation for 10 years. But it allows us to control the time of day. We know exactly when water is being used, how much, and how much we have to make. So it allows us to really predict the usage very accurately to take advantage of the best run scenario for the utilities. This one saved about $10,000 a year in operation and somewhere around 60 tons of carbon. So the greenhouse gas reduction is a big deal. We're much like Ryan was mentioning, we've already switched to 513A. Turns out it's pretty much identical to 134A that we originally used, except the global warming numbers down by about 60%. And all the functions, it functions just like you're using 134A, oils the same, all that stuff. And so we were able to produce an operating chart here, which shows that we're as efficient or more efficient than any heat pump in the world at any climatic temperature. So because the whole building is the whole unit is inside the building, we don't worry about what the temperature is outside. So we have a very constant operating range. The wastewater stays about 75 degrees and makes for a very uniform operation over time. This is the little sizing chart. And the conclusions we came up with is that we can produce 100% of the hot water for buildings. Average COP is 3.5 or better. The refrigerant changeout was pretty easy. 100% reduction of the global warming of the CO2, 60% global warming, and 60% savings on energy. And if you think of all of that water leaving the building with the heat in it from the hot water, that's enough heat over the life of the unit to melt about 60,000 tons of ice, and as it goes into the oceans and rivers. So that's an American football field about 75 feet deep in ice. And what really made it work for me is the thought of continually reusing the energy that we recover. So the great part is that you use the energy, goes down the drain, we recover it, and you reuse it again. And you can never run out of energy. As you need heat, you're using hot water, and it's coming back down the drain. So long life cycle, because it's not exposed to the outdoors. Yearly efficiency is amazing. Long life, like I say, and high customer acceptance. And when I was in the geothermal heat pump business and heat pumps in general, people wanted to know the way heat pumps work, the vapor condensation cycle, all that stuff. When I mention sewage heat recovery, people tend to go, yeah, I always knew there was a lot of heat in there. And so we, like I say, in summary, we are as good or better than any heat pump on the market. Nice, simple proposition to continually reuse the heat. No smell, no muss, no fuss, and the utilities love us because they can predict the loads. So I'm not as long-winded as those two guys in front of me. So that's the Piranha story. We were presenting to the Congressional Energy and Water Committee this morning. So I do believe there's an opportunity to be had, and all heat pumps are good. I'm a big proponent of heat pumps, and we're just one of many that are really good. I love Comac and Nyle and everybody. So I'm like Ryan. My mission is to make the world better, and my contribution is to put my hand in a pile of crap and save people money. So thank you so much, and thanks, Jeff.
Great. Thank you, Lynn. Appreciate it. There is one question here from somebody from the audience. Do you separate toilet flows from other wastewater in buildings serving your wastewater storage tanks?
No, it's black water. We use solid handlings, pump, etc. So the Piranha has a wide gap heat exchanger that's about 32 inches wide. So nothing plugs it, and what comes in goes out. So very, very simple. The bigger shark stuff, we do have the best technology in the world for separating paper, etc. So the bigger stuff, yes. The Piranha, no. So
this is a follow-on for Lynn. Are you keeping the gray, black, and fresh waters all separate in the system, or is it all just mixed into one single tank?
Yeah, it's black water. So it's the sewage leaving. One of the important things, too, that I didn't mention is that it's all gravity feed from the building. So installing our system cannot plug the sewer flow from the building.
Okay, and there's another question here regarding the sewer flow. Is there any kind of penalty or challenge with introducing cooler water into a municipal sewage system?
No, and the funny thing is once the cycle's been in operation for a while, the sewer tank stays a very constant temperature, because as you're using hot water, it's coming back into the tank. So we really, just on the first load of hot water, do we really affect the leaving temperature. But I think if you looked into it, most municipalities now are faced with finding ways to cool the wastewater that they have to treat. So it's a major problem, especially on the West Coast. And in the world, there's about 938 trillion liters of sewage a year. So that's about 200 trillion gallons a year. So like Seattle's got 700 million gallons a day. New York's got 1.4 billion gallons a day. It's all been heated 30 degrees. So there's a tremendous amount of energy that we're just throwing away that we don't have to.
Okay, great. Well, I think what I'm going to do is move on to some general questions. We've got roughly 10 minutes left in this session. And, thank you, Lynn, or Rebecca. This is some upcoming conferences that are going to be available for anybody. So the summer session is still going to be virtual, so no Asilomar this year. But we hope to have the Water Forum live in person in Atlanta next year. So it should be an exciting time. I also have a couple questions in general for the panel, and I'd like to open these up. How are you planning to address a fully packaged system? And let's just sort of go in the rank order of the people, the speakers. So Nyle, how are you planning on addressing a fully packaged system? Everybody can turn on their monitors as well.
Okay. Yeah, so our approach to that is very much customer-centric and customer-driven, where we are able to offer the heat pumps, the tanks, and the piping connections, pumps, controls, valves, et cetera. And we can provide those pieces and parts sort of a la carte as loose components, or we can work with engineers, depending on site requirements, to skid up the various components in various levels. So we could have a completed skid that's designed to be delivered on a semi-truck flatbed that gets craned up to a rooftop with a single point electrical and plumbing connection, and then it's ready to commission. Or perhaps, as I explained earlier, it might be split, where you've got the tanks in one place and the heat pumps in another. Or perhaps, there are small entryways to get into the mechanical spaces. And so you're going to be buying all of the pieces and parts individually and then assembling them on site.
Okay. Kane?
So we're following a similar approach. So we'll have the heat pump units themselves. Through our design software, the engineer will be laying out the number of tanks and the size of those tanks, their total hot water storage capacity requirements. We'll be providing the tanks, the secondary heat exchanger, the unit itself, the secondary side pump as a package. So it will be purchased together as one package. The swing tank will be optional. If it's a retrofit, then they'll have the option to reuse the existing tanks in the building if they're suitable. If not, we can provide the swing tank as well. So we want to provide a solution with a specific set of schematics to have really a repeatable solution that can be repeated time and time again, with good operation and energy efficiency, and provide that solution all the way up to the mixing valve, and in some cases including the mixing valve as well.
Great. And Lynn?
And we supplied just the Piranha and the drawings and stuff to put it in. We like to work with quality mechanical contractors to do anything outside of our units. So that's more of our strategy. We will supply the specs for what you need, and then contractors install it.
Okay. And a little bit of sort of verifying from people using and building systems like this. The EcoSizer has been talked about quite a bit. It was a joint venture between SMUD, Southern California Edison, with the work being done by Ecotope. Does the EcoSizer get used by each and every one of you? Let's sort of do in reverse order. Lynn, have you even looked at that?
Yeah, I'd never heard of it till you brought it up, Jeff, but I have since checked it out, and Sean and his group there, they match ours pretty much identically. So yeah, it's a great tool.
Okay. And Kane?
Yeah, so the EcoSizer tool is something that we'll be directing mechanical engineers in the field to use, especially for the multifamily applications, which is what it's really geared towards today, and to use those outputs from the tool as the inputs into our design software. And then if there's any specific application types that are not covered, then we'll work through with our applications group. But I see the EcoSizer tool and the evolution of that as being something that's really key to help adoption in the industry. So,
okay, Ryan.
Yeah, I'd echo what both of them have said, Kane and Lynn. It's a fantastic tool. We've compared it to the sizing tool and calculator that we have, modeling software for determining storage, and it matches up really well and has some advanced functionality. So we have already been directing engineers and others to that site.
Okay. And as you look at each one of you touched a little bit about demand response. Are you considering demand response as being a key driver with your products or a secondary driver? And if so, if it's a primary driver, how are you planning on reporting that or giving information to your customers and or the utilities? Let's start with Kane.
Yeah, so I think it's really going to depend on the market, the area of the country. Obviously, we serve all 50 states in the U.S. I see areas where demand response really will be a key driver, especially in the coming years. To enable that to happen, then we have an interface that we're looking to work with SkyCentric. So through SkyCentric CTA 2045 device, that'll be the module which will accept the utility commands, and then from there we'll interpret those commands and then program our unit to provide the best possible operation to ensure you've always got hot water available, and we know what hot water is available at any one time, and to operate the unit within those most cost-efficient points in time for the customer as well. Key to that, obviously, is the initial design of the system and making sure you're sizing to allow the system to shut down for those periods of time, whether it be 2, 3 hours, 4, 5, 6 hours, however many hours are those events that we may come across. The sizing really is key. So it's not really something we'd recommend necessarily adding to a system unless it's been sized for it in the first place. And then monitoring of that, we'll have a cloud solution through our Building Connect Plus platform, so customers will have access to that information, and if necessary, if they needed to perform overrides, then they would have that capability. Well, there's enough smarts in the system to really ensure that the hot water is always there when it's needed, and at the same time, during those load shift events, demand response events, we're able to accommodate the utilities commands.
Great. Lynn, how about you? We may have lost Lynn. Well, let's go ahead to Ryan and see what you mentioned packetized and talk about a little bit about the value proposition.
Yeah, this is, I think, going to become a major component of this technology solution for a couple of reasons. First of all, we can't just infinitely add more and more load to the electric grid without it being smart. I see, the smart behavior algorithms and the ability to learn and predict based on weather and renewable generation as really a key enabler of this technology, which is going to allow the electric grid to support the additional load of water heating and HVAC that's currently handled by gas and other energy sources. So it's an enabling technology from a technical standpoint, and from a financial standpoint, I see it as a major barrier, knocking down that barrier of the cost, the upfront cost, and then the operational cost because of the difference in energy prices. So I view this as a big lever, and in terms of system capabilities, there's more that we can do beyond just demand response and time of use schedules. And that's one of the reasons that we partnered with Packetized Energy, because there's actually some other types of grid services that can be provided that go way beyond just turning the unit on and off based on energy availability or prices.
Okay, great. Lynn, did you want to comment on anything, or should we close this down and move to Zoom? I think we might have lost him. Actually, he doesn't show up here. Okay, so for everybody who is going to join us at the Zoom, there should be a link on your hub on how to get into that Zoom meeting, and we will all be there directly. So it'll take us a couple minutes to all assemble there, and then we'll continue this discussion. I want to thank everybody, all the speakers, for presenting their great presentations, and also the audience for participating and providing some good questions. So thank you all.